Okay, you've definitely seen this equation before. It was probably on a chalkboard back in high school. But what if I told you that y equals mx plus b isn't just a bit of algebra homework? What if it's kind of the hidden code for almost everything, from the laws of physics to the logic of AI?
So you remember the letters, sure, but do you know the story they tell? We're going to dig in and find out why this simple formula is truly one of the most powerful and profound tools we have for understanding our universe. To really get it, we've got to go back a bit. We need to see how this equation became more than just math, how it became a language for translating the world of shapes into the world of symbols. You know, for the longest time, geometry, so shapes, and algebra, symbols and numbers, were like two totally different worlds. They didn't talk to each other. Then, in 1637, this guy René Descartes comes along and publishes La Géométrie, and boom, everything changes. He basically said any shape can be described by an equation, and by doing that, he created this universal language for science, and yeah, he paved the way for calculus. Okay, so the real magic here is in the super simple story it tells. It's basically a narrative with just two main characters. Yeah, seriously, think of it like a story. On one side, you've got M, the slope. That's the engine of the story, right? It's the action, the dynamic part that tells us how fast and in what direction things are moving. And on the other side, you've got B, the y-intercept. That's the solid ground, the unchanging foundation. It's the fixed point where our story always begins. Okay, let's make this super concrete. Picture a savings account. You start with 20 bucks. That's your B, your initial condition. Then you decide you're going to save $5 every single week. That's your M, that constant rate of change. So the total amount of money Y you have after X weeks is perfectly described by Y equals 5X plus 20, a starting point and a steady rate of change. That's it. That's the whole story. And once you see this pattern, this starting point plus a steady rate, man, you start seeing it everywhere. A mechanic's bill, it starts with a fixed fee, that's B, and adds an hourly rate, that's M. A plant starts at some initial height, it's B, and then grows at a steady rate per day, it's M. Once this clicks, you just can't unsee it. So you might be wondering, why are we so obsessed with this simple model? Is it just easier? Well, no, it's actually way deeper than that. It's tied to a really core philosophical idea about how we search for truth. It comes down to this principle called Occam's razor. The basic idea is that the simplest explanation is usually the best place to start. And you really can't get any simpler than a straight line to describe a relationship between two things. It's our natural default. In science, this preference for simplicity is called parsimony, and it's so important. Scientists start with a linear model because it makes these really clear, testable predictions. And here's the key. It's easy to prove wrong. Now, that might sound bad, but in science, that's a feature, not a bug. It's the fastest way to learn and figure things out. There's this concept in statistics called the bias-variance trade-off. Think of it like this. A super complex, wiggly model might fit the data you have perfectly, but it's probably just memorize all the random noise in that data. We call that overfitting. A simple line, though? It's designed to ignore the noise and look for the real underlying signal. It's more stable, it's more robust. And because it's so simple and reliable, this little equation has become the absolute workhorse for, well, pretty much everything. Let's fire off a few examples. Take physics. Ohm's law. Voltage equals resistance times current. That's just Y equals mx. It's a foundational law of all electronics. And yep, it's a straight line. Or how about business? The total cost to make something is your fixed costs, that's your B, your starting point, plus the cost for each individual item, your M, times how many you make. It's Y equals mx plus B all over again. And this one is huge. It is the absolute bedrock of so much of modern AI. A technique called linear regression is basically just finding the line of best fit through a bunch of data to make predictions about, well, anything from house prices to company sales. But here's what's so critical, especially today. A linear model is what we call a white box. We can see inside, we know exactly why it makes a certain prediction. With a lot of complex AI, these so-called black boxes, you just get an answer with no explanation. And in high-stakes fields like medicine or finance, that's a massive risk you just can't take. Okay, so the line is great for simple, steady systems. But here is the most incredible part. The real mind bender. Its biggest superpower is actually helping us understand things that are not simple at all. things that are curvy.
Just picture any complex, winding, smooth curve you can possibly imagine.
Because the huge, world-changing insight of calculus is that any curve like that is really just made up of a bunch of tiny, infinitely small straight lines. If you zoom in far enough, any curve starts to look flat.
This is the magic trick of calculus. It's called the tangent line approximation. You just pick a point on a super complex curve, you zoom in, like way in, and suddenly it looks just like a straight line. And we can use our simple y=mx+b to understand that tiny little piece of a much bigger, much more complicated puzzle. We're using simplicity to decode complexity. Now, of course, we have to be honest here. The model isn't perfect. It breaks down anytime the rate of change itself is changing. The arc of a thrown baseball isn't a line, it's a parabola. Compound interest isn't linear, it's exponential. True wisdom is knowing when your favorite tool isn't the right one for the job. But even with those limits, the linear model is still our default. It's our starting point. It's our baseline for trying to make sense of the world around us. It's the first story we tell about data, the simplest story. And that leaves us with one last big question to think about. If a straight line is the simplest story, what incredible truths might we be missing in all the beautiful, complex curves that lie just beyond it?